In this video, we're going to review the counting methods, specifically those that are used for the Unit 1 and 2 Math Methods curriculum. This means having a look at the addition and multiplication principles, as well as some of the more complicated scenarios like arrangements, permutations, and selections. For those who don't know me, my name is Chris Iannazzoni. I've been tutoring for around 2 years now, and I release these class recordings in the hopes that it helps you understand the topics a little bit better. If you would like to join these classes, then there's a link in the description for you to check out. Otherwise, enjoy. Alrighty, let's make a start. So this will be the second run through of the counting methods side of probability type stuff. We'll look at the addition and multiplication principles. This is all about trying to figure out the number of choices there are in a given scenario. And then we dive into more complicated versions of those, such as arrangements, permutations, and selections, all of which is helping us figure out the number of possible outcomes in a given scenario, which we can then use to calculate probabilities from. So first up, it's fairly fundamental, addition principle. So basically, if you have m number of choices for one option and n number of choices for another, if those are mutually exclusive, you cannot have both choices at any given time, then you just add the number of choices. For example, if you wanted to choose a single main meal off of a menu, then it doesn't matter that there's 3 pizzas and 2 pastas, you still consider it just 5 total choices for your main meal. If you're only allowed to choose one from a total set of options, it doesn't matter how many times you break that set down into other things, those options will remain as a collective rather than individual. So you just add the results together. For multiplication principle, kind of similar, but this time you're dealing with things that are happening in sequence. So under those circumstances, you would multiply when it's in sequence. The example that I have here is choosing to either walk or drive to the gym, and then once you're at the gym, you can choose to do either cardio or weights. And so that's 2 choices for mode of travel, and that's 2 choices for exercise. Those choices are made in sequence, hence they will multiply. And if you wanted to see what the combinations were, it would be walk and cardio, walk and weights, or drive and weights. What you'll find is that tree diagrams can be pretty nice for visualizing this sort of thing, although as the number of choices gets larger and larger, this becomes less and less effective. So if you have a small number of choices, it can be nice, but otherwise not really super practical. That's pretty much it for addition and multiplication principle. As far as how to apply that to probability, it helps us find capital X and capital N, where capital X is the number of desirable outcomes and capital N is the total number of possible outcomes. So, for example, Jess is choosing 6 subjects for Year 11 and 3 of them have already been chosen. That means there's 3 left to choose for the rest of the subjects. For the remaining 3, she'll choose one of the 3 maths, one of the 2 arts, and either one of the 5 languages or one of the 3 sciences. First question, what is the total number of possible subject selections? Well, if there's no other further restrictions beyond what was just suggested there, we have 3 choices for that 4th subject. We've got 2 choices for that 5th one, and we've got 5 languages and 3 sciences, but because we can only pick one of those, that's when the addition principle kind of applies. We can only pick one of a collective, and so we add those 2 results together, which is how we have 8 choices for the final subject. From there, considering that we're making these choices in sequence, so we have a math, an art, and then one of these, it'll be multiplication principle. So you multiply the 3 by the 2 by the 8, that's going to give you 48 total possible outcomes. If there's any questions at any time, let me know. Next up, probability of selecting a science. So what we've just found is capital N, the number of total possible outcomes. This is finding capital X. We're looking for specifically the number of outcomes that have a science in them. There's a couple of ways you can do this. One of which is to look at the full set of combinations and then think how many of those have a science involved. Or you could simplify things and just look at the section where sciences could even be picked at all. And so if you simply just look at the stage where you would have an option of selecting a science, then you've got 8 total things that you could choose, 3 of which are sciences. So that's going to give you a 3 out of 8. That'd be the easiest way to go about that one. Otherwise, you'd have to figure out how many of these 48 total combinations contain sciences. That gets a little bit more complicated. Those are the basics there. Anything you'd like me to dive into any deeper? Okay, next up, we look at how to, well, not overcomplicate things, but how to handle already more complicated examples. So, first up, this idea of arrangements. Arrangement simply tells us how many ways can we arrange or order a set of objects that we have. Those objects could be whatever you want. The example I give here, suppose you have a set of 3 possible objects, and we want to figure out how many ways can I order those objects. Well, an obvious way to go about that would just be to literally count out the possibilities. If you have 3 different colored blocks, red, green, and blue, then figuring out the sample space by just toggling each of the letters over and over again until you get all the unique combinations wouldn't be the end of the world. What gets more complicated is when you have 10 objects. That's a lot more counting to be done. In fact, if we take a sneak peek at how many combinations there are, pretty sure that's 3 million. Yeah, 3.6 million. So good luck with that. So what we do is, my recommendation for when they get complicated like this is to consider the number of positions available or slots available for those objects. In this case, since we have 10 objects and we want to arrange them, we're putting them in 10 positions, basically. 10 objects, 10 positions for those objects. So you start out with a little grid like this. From there, you simply consider how many options do I have for that first position. Well, I've got 10 objects, and therefore I have 10 possibilities to put in that first spot. So that's going to be a 10. From there, you now consider how many choices do I have for the next spot. Well, since I've already used one of my objects up, I've only got 9 left over. And so I'm going to put 9 in the next box. Fundamentally, you can see how this pattern would continue. Every time I place one, I lose one of the blocks, and therefore I decrement the number of possible choices I have for that next position. Now the trick here is that every time you do these kinds of arrays here, this is choices made in sequence. You can think of it as saying, I've got 10 choices for that first one, then I've got 9 choices for the second, then I've got 8 for the third. It's all being made in sequence. Hence, we take all these numbers and just multiply them together. And that's going to give us that 3.6 million-ish. 3.6 million. This is more formally known as a factorial. Specifically, this would be 10 factorial. Basically, a factorial is just anything that has a starting number and is subsequently multiplied over and over again by a decremented by 1 version of that number. So 10, 9, 8, 7, 6. Or you could have like 5 factorial, which is 5, 4, 3, 2, 1. That's the pattern for factorials. So that's arrangements there. As far as what happens if you want to arrange into a smaller number of groups, that's what we call permutations. So again, we could say I have 10 objects, in this case 10 books, but let's say I only have room on my shelf for 3 new books rather than 10. From there, we want to figure out how many possible, you could say arrangements or you could say permutations, how many are available now. Well, we now have 3 positions available for those things. And if I look behind me, I've got 10 books to put in that first position. Then I've got 9 left over for the second. Then I've got 8 left over for the third, as far as my options go. It's the exact same idea. All we've fundamentally done is just truncate the number of positions or just cut off any other further positions from that. If you have a significantly larger number of options, so let's say you don't have space on your paper for like 10 different cells, then what you can start doing is using the actual permutations equation itself. which is simply n is the number of objects or things that you have, and r is the number of positions for those objects, if we're using the same metaphor. So how that works is we have 10 books and we have 3 positions to put them in, and so you have 10 factorial divided by 7 factorial. Now, as far as how to simplify that, all you would do is expand out what you have. So 10 factorial would be 10 by 9 by 8 by 7 and so on. 7 factorial would be 7 by 6 by 5 by 4 by so on and so forth. You don't have to go all the way to the end, you just have to get it to a spot where you can clearly see the pattern. From there, you'll be able to identify what terms cancel out, and in this case it's going to be everything from 7 onwards. That's going to give you that 10 by 9 by 8, which, well, equals 720, and that's effectively the same thing as what we had from our position metaphor instead. Any questions about that one so far? Okay. If we apply it to another example, we have 3 options. We have vanilla, chocolate, or strawberry for, I'm assuming, like, let's say ice cream. And we're supposed to select 2 different flavors. So if we want to figure out the number of combinations that are available to us there, well, we've got 2 positions to put those flavors in, and initially we have 3 choices for that first position. Then, because we have to select a different flavor, we can't select the same one, the next number of options would be 2, right? You've only got 2 remaining options for that second slot. And so finally, you've got 3 more 2, which equals 6, or you could just do permutations equation, whichever one makes more sense for you for that moment. One of the things to highlight is that the permutations equation comes with these, you can kind of think of them as duplicates. It really depends on the scenario. Like, for example, we've got chocolate and vanilla here, but we've also got vanilla and chocolate as another combination. So suffice to say, when you do permutations, the number of combinations that you get from that result will have the order as a unique property. So chocolate and vanilla is seen as different to vanilla and chocolate, at least as far as the permutations equation is concerned. Your scenario might not care about that. Your scenario might care about that. It all depends on what's being said in the question, really. This one didn't even really have a question. It was more so just a hypothetical here. So we'll look into it a bit later, how we can remove those duplicate combinations, but it's worth highlighting initially that that's what permutations gives. As far as how to apply this to probability, this is where we start getting more complicated kinds of examples. So in this case, yeah?
Chris, sorry, I was just writing the notes, and you know the permutations equation?
Yeah.
You know the R, like what does R stand for?
The number, so you can think of it a couple of different ways. If you like this sort of positions metaphor thing I've got going on, R is the number of positions that are available. Alternatively, R could be the number of choices you want to make. So, for example, you've got 10 books and I want to choose 3 of them. R would be the number of choices you're making from that sample size.
Yeah, cool. Thanks.
No worries. Okay, so in this example here, we have 10 seats on a plane and 3 passengers. Seats are chosen at random by those 3 passengers. The question we're being asked is, what is the probability that the 2 rear seats remain empty? That can kind of suck as a question. As far as how we handle these sorts of situations, this kind of scenario feels a bit backwards, because when we think about assigning people to seats, if we do it that way, we would say we have 10 positions available, but only 3 passengers to put them in. It doesn't really work out that well if you think of it that way. So instead, in this case, we have to think of the reverse. We're assigning seats to passengers. That way, we can have our 3 possibilities, and then, well, our 3 positions, and then assigning the number of possible seats to those passengers. this sort of thing only really works if you have a bigger n than r. Otherwise, permutations or this won't really help all that much. But otherwise, if we're looking for just total possible combinations, we can pretty much ignore this part. We're just focusing on capital N, total number of combinations. So there'd be 10 possible seats for the first passenger, then 9, then 8. Because, well, we're assuming passengers can't quite just sit on each other in this case. Now, what's interesting about handling the restriction is you've got to get kind of creative with it. And this kind of comes with exposure. You just got to kind of do a lot of these questions to start realizing what kind of tactics work and what don't. One of the things I found well for this kind of thing is to, in this case, we're basically trying to force the two rear seats to remain empty. And so one of the ways you can do that is simply say, okay, they're just not going to be in my sample size anymore. So when I think about assigning my seats to those passengers, instead of having 10 possibilities for them, I'm now just going to have 8 possibilities to them. It didn't actually matter that it was the rear seats that had to remain empty, because as far as combinations are concerned, the underlying math doesn't really care where the seat is located. It just cares that there's 2 less that can be allocated, which is why we start at 8 and then decrement from there. That's going to give you 336 possible combinations where not even necessarily the rear seats are empty, but where 2 seats would be empty, and that is sufficient because it's effectively the same thing. So you do your division, so number of combinations that are desired, 336, divided by total number of combinations, 720, and then if you simplify that down, you're just going to get 7 out of 15. Anything to clarify there? Okay, next up, kind of the reverse situation. What is the probability that the 2 rear seats are filled? Well, under these circumstances, and I kind of probably should have said it for the first one as well, which is you want to address the restriction first. We did do that in the previous one by knocking off the seats before assigning them. But the overall idea is that you try to address whatever the restriction is first and then backfill from there. So in this case, if the restriction is to make sure that the 2 rear seats are filled, then that means I want to fill those seats as early as possible. So I've got my 3 people that I can choose from. That means I have 3 choices for one of those rear seats. Then I have 2 choices for the next seat. And lastly, well, that final passenger can sit wherever they please. There's 8 total choices after that. We've already filled in those 2 rear seats. That's what I mean by backfill. You just fill in everything else after the restriction has already been met. So once again, these things are being made in sequence, multiply it up together, and then, well, our total hasn't changed. This was part B of the same question. Total number of combinations shouldn't change from part to part unless they do something really crazy, which, I mean, they kind of do in year 12. They do like to change between probability types, but the shift is, I think it's obvious enough. And I don't think many of my students have found it non-obvious when it shifts the type of probability question. Yeah, and then obviously you just simplify the fraction. That's arrangements and also how you do permutations. So we looked at how to arrange things when you have same number of objects as positions for it. And we've also looked at how to put them into less positions available for those objects. That'll be the permutations equation here. Or obviously you can do the position, the visual version of that. Worth highlighting, once again, you use this type of equation if the order of the choices is important. The typical example could be from numbers, right? If I put a 1 and a 2 next to each other, that's 12. If I do it the other way around, that's 21. The order in which I write those things matters a lot, so we would use permutations. Anything to clarify there? All right. Last Last up will be selections. So I kind of alluded to it earlier. There is a way to remove those duplicate combinations if the order in which things happen don't matter. This is often seen in teams of people, where if I say a team of Dan and Kim, it's the same as if I had said a team of Kim and Dan. It doesn't matter what order those names are written in, it's still those two people on the same team. So under those kinds of circumstances, where the order is irrelevant, we would use the selections equation, which is a very slightly different version of the permutations equation. There's this further division by r factorial, and you can kind of think of that as just removing all the duplicate combinations. You'll sometimes see this referred to as NCR, or using this kind of notation. This one will show up on the CAS. I think I might have seen this on the Casio before, although I could just be mistaking that for the for matrices, which is no longer in the study design. But yeah, these are the kind of notations that they just mean this. In fact, yeah, maybe this is on, I think this is on the formula sheet. Yeah, this one's on the formula sheet. Anyway, so in this example, we have a group of 4 people, and specifically, what are we actually doing? How many teams we can make? Yeah, okay, so we have our 4 people, and we want to know how many teams we could possibly make. So we're still going to consider these things as being done in sequence, but we're going to be using our selections equation to calculate those number of choices in sequence. So in this case, the first team would have 4 people to choose from and 2 selections to make, right? If you've got 4 people, you have to have teams of 2. We're assuming even sized teams. So you would simply chuck in n equals 4 and r equals 2. N equals 4 because that's the number of people you have available, and r equals 2 because that's the number that you're choosing from that sample size. If you simplify that all the way down, you'll get 6, hence the first choice in our sequence is going to be 6. From there, to create the second team, there's only 2 people left to choose from and 2 selections to make. So this one should be fairly obvious when you think about it, that there's only going to be one possible combination. If 2 people were already selected for that previous team, then there's only 2 left, and so only one way to organize those people. So this is probably more complicated than you need, but I do still like it in the sense that it's using the same sort of techniques you see in the previous notes. A lot of what we run into with these kinds of questions is there's a lot of ways you could do these. And so what I've tried to do with these notes here is just refine it down to, like, if you just follow these basic principles, you'll get the vast majority of things right, and only the most strangest and complicated questions will maybe have to force you to improvise a little bit. But okay, so these are choices made in sequence. We selected team 1, then team 2, hence we multiply across. 6 by 1 is going to get us 6. And if we were to calculate actually look at all the possible combinations there, there's that list, should you be interested in seeing what those would actually correspond to. As far as applying this to probability, up until now, we've seen more or less 3 different ways of going about things. You could use the multiplication principle, just without any of the other stuff involved. That would be where you do your positions, where you have r number of positions for a thing and n total choices, or n as your total sample size. You would use that, the multiplication principle, if the choices in the sample space can be repeated. You can use it for other things if you like, although what I've done with this little criteria here is say which would be most effective in any given scenario. If the choices in the sample space can be repeated, sort of like those things with replacement, one of the examples I give is drawing names out of a hat. If I have several names in a hat, I draw one out, I read it, and I put it back, shuffle it up a bit, nothing has changed from trial to trial. I can pick that same name out again. And so if that's the kind of experiment that you have, then consider using a multiplication principle approach, because the number of trials, or the number of choices per trial, is constant. It's kind of fixed there. Whereas with permutations and selections, the whole point was that it decrements every single time. We're using factorials. And if you remember, factorials came from this, where the number of choices at every stage was decrementing. So we can only use arrangements, permutations, or selections when those choices are decrementing. On that note, if your choices cannot be repeated, so they are decrementing, and the order matters, so AB being different to BA, or 12 being different to 21, then you would use permutations. If choices still cannot be repeated and the order doesn't matter, so that was like the team's example, then you would use combinations or selections. Those mean the same thing. We're just going to see a few examples of this. Kind of hard to talk about that high level, but those are the main sort of things I'd be considering when choosing which technique to use. Here's an example of choices being repeated. So we have a number of digits, 0 through 9, and we want to figure out the number of possible 4-digit numbers that can be formed. We're not told that we have to use unique numbers every single time. We could have 4 zeros in a row, for instance. Wait, sorry, this isn't pin codes, this is actual numbers, my bad. I mean like actual numbers, so it would be like 1,000 or 102, anything like that. You can't just have leading zeros. I got mixed up with the pin codes example. So okay, with that in mind, we have to figure out how many choices I have for each of those digits. So the reason I'm saying there's only 9 selections for the first digit is because your number can't start with 0. Real numbers don't do that. Pin codes, however, would. So there's a bit of a nuance there. But in this case, since it's numbers, there's going to be 9 selections for that first digit. And then since there's no further restrictions on what numbers can look like, there's going to be 10 choices for the remaining 3 digits repeated. 9 by 10 by 10 by 10, you're going to have 9,000 total outcomes. Here's an example of where choices can't be repeated and the order matters. So in this case, very similar example, but this time we can't repeat numbers. We can't have like 3 zeros at the end, for instance. Very similar circumstance, except even though we're starting with 9 selections for that first digit, now when we consider the second digit, there's still only going to be 9 options for us. We've increased the number of options by 1 because now we're allowed to start, or now we're allowed to have a 0 in it, but we've decremented by 1 because whatever number we chose before, we cannot now use again. That's why it's 9 and then 9. The rest of it's making enough sense after that though. We've chosen 2 digits, that means there's only 8 left for the third, and then 7 left for the last. Effectively, this could be thought of as doing 9 multiplied by a permutations equation. So you can see the permutations and multiplication principle kind of play a role together. They're effectively the same thing. And yeah, that's effectively the same thing as just if you had done the flat out multiplication principle idea. Okay. And then lastly, usually it's around teams when you want to use this selections equation. Order does not matter for the teams. So, team of 3 boys, 3 girls is to be chosen from a group of 8 boys and 5 girls. How many different teams are possible? Well, similar to before, we could choose our team of boys first, then our team of girls next, or vice versa. It doesn't really matter which way you think about it. The point being is that it's made in sequence. So whatever the number of boys, the number of girls combinations are, at the end you would multiply. As far as how to find those combinations, that's when you look at each of those individual groups and you use the selections equation. There were 8 boys, we're choosing 3. There were 5 girls, we're choosing 3. So you plug those into your equations, simplify things down, and then those become the numbers that you multiply together. And so that pretty much brings us to how we solve these kinds of probability questions. Usually, you start by trying to find the total number of possible combinations in your scenario. You'll be using either multiplication principle, permutations, or selections to achieve that. Part 2 is where it gets a bit trickier. where we're now looking for the number of combinations that meet your probability or desired number of outcomes. It's kind of unlikely you'll be able to just use any of these out of the box as is. Multiplication principle tends to be a bit dominant around here. Like if we consider the plain example with having rear seats filled or rear seats empty, a lot of it really comes down to just sort of thinking about how many choices do I have per position. Trying to apply permutations or selections to something like this, kind of difficult. So usually this one here, multiplication principle, reigns king. And then step 3 is really easy. Once you have both of those numbers, you just divide them. You've got number of combinations that meet your target probability, number of total combinations, divide those two things. Is there anything I should clarify further before we get into some questions? We're going to work our way up to that, by the way. We're not going to go straight into the hardest questions there. Okay. So what I'll quickly do is, got the notes up here. Have a read of question 1. Don't think too hard about that. And in the meantime, I'm going to take off some layers because it's getting hot in here. I'll be 1 second. All right, I am back. So, question 1. How many choices of book are possible if one book is selected from any of the following? Give you a moment to have a think about what's going on there and what you might apply. These are supposed to be the fundamental ones, so I wouldn't say you should think too hard about what's going on here. This is in the addition and multiplication rule chapter.
Is the answer to 1A just 1 out of 11?
So this one's looking specifically for number of choices, not a probability.
Oh,
So
so 2 choices.
11. So you had it kind of right. You just turned it into a probability instead. Yeah. So it says find out how many choices are possible if one book is to be selected from 8 novels or 3 dictionaries. So how many choices do you have for that one book? That'll be the addition of those two things. If it had asked what's the probability of selecting any given book, then that 1 out of 11 choice or answer would be correct. Yeah. Now from there, B, C, D shouldn't be too crazy. So feel free to do those if you like. Otherwise, we can move on to question 2. Yeah, even just 2A will be fine there. $60 is correct. Yeah. So for everyone else, this was choices made in sequence. So you're choosing an entree, then a main, then a dessert. So you take the numbers that are associated with entree, main, and dessert, and you just multiply them across. Yeah, that's all that's going on there. Okay, next up, let's see, is there anything? Yeah. Question 3 I remember being interesting. We'll do both of these because part B is the more interesting one. In fact, yeah, you can go straight to B if you like. The answer to A isn't required. Or I should say, it isn't required to answer B. You don't need the answer from A for B.
Chris, is the answer to 3B 160?
160 is correct. There's a couple ways you could do that. I'm curious which one you used.
So in like 3A, right, I got 128 by just using the multiplication principle.
Yep.
But I didn't draw it out, but in my head I just visualized like a tree diagram.
Mm-hmm.
And then next to entree, you just add one more choice, which is the omit.
Yeah,
So
that's
then
good.
you just multiply 5, 8, and 4 to get 160.
Precisely, yeah. So the choice to omit an entree is in and of itself a choice. So instead of having it was four choices for entree, you now have 5 choices for entree. That's one way of doing it. The other way is that you can actually split that up into 2 separate groups, where you figure out the number of combinations that exist with an entree, and then you find the number of combinations that exist without the entree at all. So what that would look like is as follows. If I change that screen share over, what was described was method 1. What I'm describing now is method 2, which is you can split the scenario up into groups. So number of combinations with an number of combinations with an entree. That's going to be the answer to part A, which is the 128 combinations. And then from there, you just decrement all the or you ignore the fact that entree could even be included. And so you just have 8 by 4 instead of 5 by 8 by 4. And from there, well, you just add those 2 sections together. That's another way of handling it that's quite common. Okay, screen share. Yep, screen share should be fixed up now. Let's see, is there anything else that's interesting? There was this one that we did last time. Let's see if we remember what was going on here. It was all about traveling from Melbourne to Brisbane. There was a whole bunch of different scenarios here. So we'll do question 6. Worth pointing out, these kinds of paragraphs are quite common. Go ahead.
Would it be 23?
23 is pretty close. So I wonder if there's maybe just an addition error there. What was the idea? That's
I'm not sure if that's correct or not.
Well, no, 23 is close. It should be 26. So I'm just curious if there was an addition error there, or what was your idea?
Oh no, I just missed the first part. I forgot. Missed the
Oh,
fly directly.
yeah. Well, there you go. Yeah. So
Yeah,
it was just
that
you
would have
missed the
been
mark.
26. Yeah.
Yeah, 26 is correct. Absolutely. So to explain what's going on there, once again, change the screen share over. Yeah, here we go. So there were basically three different scenarios that were posed to us that were all independent. You couldn't do all of them at the same time. And so that's why you would do the addition principle there. You got mutually exclusive choices to make. The first one was that you could fly direct. You could bus direct. That was the third one that was given. And the second one that was given was, yeah, in here. Fly Melbourne, Sydney, and then Sydney to Brisbane on bus. And it tells you the number of individual possible airlines and possible bus lines for those sections of the journey. And since those are mutually exclusive journeys, you just you add all of the individual sections together. But because this one here was done in sequence, you multiply those two. These two were done back to back on each other. That's why it's a multiplier there. That's pretty much it in a nutshell as far as how addition and multiplication principles sort of play together. You'll come across these kinds of questions where they do that. In a SAC environment, this is where underlining things gets really important. That's a big block of text, and trying to parse out the three individual stages, I'd imagine that was probably the bulk of the issue if I were to take a stab. But yeah, those are the things I'd be looking out for there. Okay, changing it back, and then we'll go straight to 11 on this one. That way I can hit some of the other chapter questions. So I'm not even necessarily looking for an answer for 11. If we can just talk about what's going on, that'll also be appropriate as well. If you can get the answer, by all means, go for it, but the methodology will be the most important thing.
Chris, I didn't get the answer, but do we set up an inequality?
We will set up an inequality, yeah, for sure.
And do we do that by multiplying all the probabilities together and then more than 1,000?
Yeah, exactly right. Yeah, you go choice by choice, kind of like how we're doing entree, main, and dessert before, but we had numbers. This time we have letters. So yeah, literally just multiply them all together. It's done in sequence. Set that greater with 1,000, and then do you have CAS on hand for that one?
Uh, no, but I can get it from my bag real
Okay,
quick.
because it'll be worth quickly checking that one out because the CAS won't give you exactly the answer you need right away. There's a bit more thinking to be done just afterwards. Yeah, there's actually two things to consider after that. You're going to get a decimal for your number. I'll let that be the hint as to what might be weird about that. Has anyone got what that decimal would be? Or do we just all not have CASs?
I got 12.27
Yeah,
if you round it up.
12.27. Yeah. So now here's the question. 12.27 for M. What's up with that? What do we have to do? What does M even mean in this case?
It's the possible values of M, like, hold on, like how many choices there are.
Yeah, M is
And I guess you just want to round this number,
yeah, okay.
the closest whole number.
Alright. So closest whole number to that. Which way do you go?
You go down.
Go down. Alright. If you plug in M equals 12 into the CAS, into your polynomial, because that's when it expands, it becomes a polynomial. Let me know what number you get. For everyone else, I'll change the screen share over. This is what we're at to so far. For everyone else, it's just do a solve, and that's what you'll get. We're saying M has to be greater than 12.27. We want to make sure that the number of choices is always greater than 1,000. What could be a potential downside of rounding down instead of rounding up?
Oh, you would have less than 1,000.
Less than 1,000, yeah. So rounding up would be a good idea. So rounding to 13. However, that also has a second barb associated with that, which is if you look at all of the spots where M exists, is M equals 13 a good idea or not? What are all the spots where M exists, and what do they correspond to in the actual scenario? We've got M choices for entree, sure. 13 choices for entree works well. What else is M associated with?
It's associated with mains and dessert.
Yeah, mains and dessert. So does M equals 13 work for both of those?
Not for main.
Yeah, not for main. Dividing 13 by 2 gets you a fraction. You can't have a fractional number of choices. So the way you'd effectively go about that is to say, oh, not only do I not round to, well, not only should I round up, but I should round up a little bit further than 13. So really, I've only got any M value greater than or equal to 14, with the restriction that m is an element of the even numbers. So that had a few barbs with it. This first part shouldn't have been too bad. It is just chucking a bunch of letters involved in a question you've seen before. The more than 1,000, sure, that was unique, but the rest of it came from being able to then rationalize and say, what does m actually mean in this circumstance? And in this case, it was tied to a lot of different things. Does anyone want me to clarify any of what's going on there any further? This will be one of the hardest ones from that chapter anyway. Okay, no worries. Let's move on. So with the remaining time we have, 10b, we're looking at now the arrangements side of things. So up the top is basics of factorials. I'll say try at least 2a. That way you can make sure you understand how to do your factorials. Now to help you with that, I'll show you an example of how, yeah, here we go. I'll do this as a screenshot so you can, well, maybe we've got to go a bit further actually. Oh, actually, no, that'll do. I'll put this in as a screenshot so you can see how factorials simplify and try apply that to question 2a. Yeah, 20 is correct. Thanks, Peter. For everyone else, I'll change the screen share over. We can see how that all works. So, basic first step. I mean, I still do this even now, which is just expand both of those factorials out as far as you need to in order to see the pattern. You don't have to go like all the way out like these. Just enough to know what cancels down at what stage, and then, well, we can see what's left is just a 5/4 as 20. In this case, everything from 7 down cancels. 0 factorial is a bit weirder. I didn't really mention this in the lesson, but 0 factorial by definition is defined as equal to 1. I remember looking into it a bit ago. I can't remember exactly why it's defined as 1. I think the rationale was just if you have 0 things, you can arrange them in one possible way. That is to say, with no arrangements at all. I think that was the rationale. I can't really remember exactly. But yeah, if you ever see 0 factorial, you just take that as equal to 1. So 0 factorial and 1 factorial tend to, well, they do have the same result. That's that one. Changing back. Let's see. Where's one that's a bit tougher? Yeah, here we go. Question. Yeah, we'll do question 8. Put in the chat, Q8.
Chris, is it 336?
336 is correct. Yeah, precisely. So for everyone else, once again, change the screen. 336 came from the permutations equation. 8 swimmers, 3 slots. That meant n equals 8, r equals 3. You can bash that out in the CAS if you like, or you can expand it all out. Either way, up to you. That'll be the same for the next few questions. Let's see. Where does it get differently? Yeah, this is where it gets a bit weirder. So question 13, you have to start thinking a bit harder as to what the restrictions are. So yeah, we'll do all of, well, as far as 13 as we can. If we don't get there, I'll explain the rest of it. Yeah, try 13. This is where you have to start thinking a bit harder. (13A) answer, yeah, 13A answer is 60. I won't change the screen share on this one. It's the exact same method as before. You would use your permutations, where it's just you've got 5 total numbers and 3 positions to put them in. So you'd use permutations, or you could just do your position metaphor, where you say, I've got 5 digits, they can go in any of these 3 spots, 5 by 4 by 3. Yeah. Part B gets a bit more interesting. This is where you'd have to lean into some more. Nah, I won't give too much of a hint there. Not yet, anyway. Yeah, maybe the hint would be think about how you can identify an even number. What is it about even numbers that you know immediately they're even? That'll help with this.
Chris, is the answer 24?
24 is correct. Yeah. How'd you go about that?
So like I just thought of it as like to have an even number, we need to have either 4 or 6 at the end.
Yep. Hmm.
And then so I took into like basically two different like cases, like the 3-digit numbers where 4 is at the end, and then the 3-digit numbers that 6 are at the end.
Yep.
And I just added the two like possibilities together.
Yeah. Yeah. Bang on. That works perfectly well. Yeah, that was like the what was it? There was another example kind of like that where you could either do the position metaphor thing or you could break it down into two discrete things. The way I had written up in the answer doc is the first of those methods. So it's like it's what you said before, which is the even numbers need to end with an even digit. So either 4 or 6, which gives you two choices in that position. And so from there, well, you just backfill, right? You've made one of the choices here. That means there's 4 left for the first digit, 3 left for the second digit. And yeah, you just multiply all the way across. That would be the other way of doing that. But nice job. Yeah, that's where it's like it gets a bit tougher for sure. Okay, we are actually about to hit time though. So what I will do is I'll explain well, actually, does anyone want to take a stab at it before I explain greater than 700? What might you have to do?
Can I try, Chris?
Yeah, yeah, go for it. What do you think we do? Or do you want to try yourself and then answer afterwards?
So obviously I'm assuming that the first number has to be 7. So in our
Yeah.
cell, wait, is it Like freestyle, like it doesn't have to be 3 digit in this case.
Uh, that's a good question. Yeah. It does actually, yeah, it doesn't have to be 3 digit anymore, does it? Yeah. Anything greater than 700. Oh, yeah, that made it much more complicated, didn't it?
All right, so then that means like the first number is just it's we can only choose seven.
Well, if it doesn't have to be 3 digit anymore, now you could have a 3 in the leading spot and then a 456. That'd be 3,456.
Oh wait, hold on.
Yeah, that's a lot more. But yes, if it was only 3 digit, then yeah, you'd be stuck with a 7 in that first spot. Yeah. So, if you want to keep thinking about it, maybe deafen, just so I can give the answer to everyone else, and then after that you can have a shot. What do you think?
Yeah, all right, cool.
Okay, cool. So basically, what we're talking about there, the way you go ahead and handle that is you consider 3, 4, and 5 digit things respectively. So what we were talking about before, the 3 digit is that the leading digit had to be 7. That gives you one choice there, and then from there you backfill. There's now 4 choices left for the second digit, 3 for the last, because you've got 5 digits in total. Then from there, 4 and 5 digits, any 4 or 5 digit number would be greater than 700, and so it would just be 5 by 4 by 3 by 2, or 5 by 4 by 3 by 2 by 1, both of which give you 120. Since these are all mutually exclusive, you cannot have both a 3, 4, or 5 digit number at the same time. You do your addition principle over there. All right, that's how that one works. If you want to stick around and see or have a go at the rest of that yourself, let me know. Otherwise, I'll leave you all to it. Take care. All right, now I have to figure out how to undeafen. Maybe I could have just deafened him myself. Nah, couldn't. Put it in the chat. How do I actually now? Yeah, I'll just hang out for a bit. I'm sure you guys will figure it out.
Wait, Chris, I was gonna ask like similar to what we did with the 3 digit and even numbers.
Mhm.
Would you want to like in this case like separate into three classes like
Mhm.
the amount of possibilities with 3 digit numbers that are greater than 700, then 4 digits and then 5 digits?
Yeah, that's exactly what you would do. That's well, at least that's what I did. I'm sure there's another way to do it, but yeah, that's a really good idea.
Okay, give me a second then. Is it 300 possibilities?
Let's find out. A little bit off. So, which of these were off for you?
Oh wait, my bad. The first one I
Oh,
didn't consider for the seven, the possibility for seven. My bad.
possibility for 7.
Like the seven has to be at the front, so
Oh, okay.
my bad.
But you said that in the beginning.
No, I
How'd you
just
forget?
no, because I left for like 2, 3 minutes when he told me to deafen. So then,
Yeah,
yeah, I
So,
forgot about it. My
sure.
bad.
Okay. Um, yeah. So the leading digit there. So everything else there was fine then. Other than that,
Yeah, I
yeah,
got 120 and then 120 for the
yeah, those are good.
second two.
Yeah, that's about it really. So yeah, damn, forgot your own idea. That sucks. Oh well. Yeah. So as far as where to get all these solutions, I've mentioned it the first time that we went through this. These are all on the classroom. It's in each of the sections on the chapter 10 stuff. Specifically it was under the counting methods probability chapter. So I know these are really tough. That's why I got written solutions to all of them. So have fun with those, I guess. All right,
Thank
I'll
you.
leave you to it. Take care.